I'd like to start by saying thank you to the organisers, actually. Really appreciate the invite. It was nice. I'm supposed to be giving this talk in a couple of weeks as well, and Chris sent me a message and said, can you do that talk here? And probably if I hadn't done it, I would be woefully underprepared for the talk in a couple of weeks. So instead, you guys get the woefully underprepared version. But hopefully it will go okay. I'm going to start with a slight flipperoo, because I suspect that often people in this position might do like a we're hiring thing. We are, but that's beside the point. But instead, I also have somebody who's looking for a job. So my partner's brother, George, put your hand up very quickly. George has just finished Makers Academy, which is, if you don't know it, it's a bit like General Assembly, one of these software engineering conversion courses. And he's a junior engineer, and he's looking for a job. If anybody has a job that they'd like to talk to him about, have a chat with him afterwards. Cool. All right. So I have some bad news. I do not know how to solve climate change. I put a title up that I thought would be headline grabbing. I have none of those answers. So you've come to the wrong place. If that's what you came for, now's the time to leave. But I do have some ideas about how we can go about reducing carbon. So we're going to hear a little bit about that. I grew up in a town called Rochester in Kent. Does anyone know Rochester? Oh, lovely, thank you. And when I was a child, my parents would drive along this main road near us, and we used to go past this cement plant over and over again. And I remember staring out of the window, looking and seeing these huge plumes of smoke billowing out of this cement plant. I remember thinking that something about the picture wasn't quite right. Interestingly, as an adult, I found out that all of that smoke was actually just water vapor, and it was fine. But actually, there is something more sinister lurking behind those water vapor fumes. A lot of dangerous chemicals are coming out of that. It's funny when you think about it. We live in a world where we have iPhones and planes and MRI scanners. But we've been generating energy in the same way for nearly 1 million years, burning stuff. That's just what we do. And it kind of just about works out when there's less than 1 billion of us on the planet. But when there's 7 billion of us, we just keep digging stuff out of the ground and burning stuff. That burning produces a lot of carbon dioxide. And carbon dioxide is like a big warm hug on the Earth. It's like we wrapped it in a blanket, and everything's getting slowly warmer. In fact, 18 of the 19 warmest years on record have all occurred since 2001. So this graph shows from 1850 onwards. I think we can see a pretty dramatic change from 2000 onwards. And it's probably no surprise that global carbon emissions are also at an all-time high. I think that one of the problems that we have as a society is that we are dependent on international committees, governments, and politicians to try and address this problem. And whether you like it or not, the world works economically. We need to find a way to have an economic solution to solve the climate change problem. How can we make it that going greener becomes cheaper? I think that a zero-carbon energy grid would be a pretty big step forwards in the fight against climate change. It probably doesn't solve climate change, but it would be a pretty massive step forwards. The problem with it is that it sounds quite easy to say, but it's actually pretty difficult to do. And to understand why, we need to understand about energy grids. So, quick show of hands, who feels like they know about how the energy grid works? Okay, good. All right, I like it. That's good. So grids are kind of really, across the whole world, are really based around one core concept, and that's that you can't really store energy. We have to balance generation and demand the whole time. And as much as we might not like coal and gas power stations, the useful thing about them is that you can slightly turn them up and turn them down. You can shovel more coal on the fire or turn up the turbine on the gas, and you get a bit more power. So if generation increases, demand increases, you're able to offset that by increasing the amount of fuel that goes into these power stations. So we're going to take a little example. We're going to look at our city here. this is, let's call it Bristol. Bristol's sort of grown up a little bit, but let's say Bristol's using 3 gigawatts of energy. In order to make sure that our network actually works, we need to have a number of power stations generating that exactly same amount. In fact, when all these numbers match, the generation and the demand match, turbines in the United Kingdom turn 50 times a second. And that's what generates the 50 hertz power that goes into all of your homes. If it's EastEnders has just finished and everyone goes and puts the kettles on or starts cooking dinner and the power goes up a little bit, we need to make sure that the generation assets that we have as a country increase the amount of power as well. It's really important that this happens to keep those turbines turning at 50 hertz. In fact, if they don't turn at 50 hertz and they just turn off by 1%, we start damaging national infrastructure. Beyond that, we can completely and catastrophically destroy the way the national grid works. It's pretty important stuff. But we've got a bit of a problem, because we all know that we need more renewables, we need more wind power, we need more solar, but we don't really control the wind and we don't control the sun. So how do we deal with the fact that these turbines are slightly dependent on, we're at the whim of nature in some way? Well, some power stations have the ability to turn up and down faster than others. Gas is okay, pretty good at being able to be turned up and turned down. So as we bring on more renewables onto the grid, we also need to make sure we've got enough power stations that we can turn up and down quickly. But unfortunately, that kind of means that we're not really getting away from the other stuff, because if every time we bring more renewables onto the grid, we need more power stations that we can turn up and down quickly, we're not really transitioning ourselves to 100% renewable. We're transitioning ourselves to 50% renewable. In fact, this problem is so acute that for the first time, really, we're starting to see prices of energy go negative. So this is a graph of the price of energy in Germany last year. You can see that around the middle of the day, Germany has a lot of solar, sun comes out, energy floods the grid in a way that Germany was not predicting, so they had other power stations on, and as a result, too much generation occurred. And the way they deal with that is by making it so that you get paid to use energy. This doesn't really apply that much to domestic markets, but if you're tapped into the wholesale market, this is what happens on a half-hourly basis. In fact, there's a guy in Germany who's built a business around just boiling water. He has huge vats of water in a field. This has become so common there that he just boils water for his job. That's what he does. And this isn't just limited to Germany. This happens in the UK. We had 6 days in a row in March this year where the price of energy went negative. So it's a pretty sorry story, really. We have all these renewables, and quite often, quite honestly, it is cheaper to keep burning coal. Turning on power stations, turning off power stations is pretty expensive business. Sometimes it's easier just to keep burning the stuff than it is to turn on and off these renewables. If you've ever wondered why sometimes when you're driving around you look at wind farms and none of them are spinning, why that happens, that's because we can't have them spinning because we've already got other stuff going on. And economically, it's not viable to turn them on. So actually, we can kind of summarize this whole problem that we have a bit of a lack of flexibility. Generation and demand are very coupled. We need some way to try and store the generation that's happening at a time when maybe we didn't need it, so that we can push it out onto the grid at a time when we do need it. And without that flexibility, unfortunately, renewables are stuck at around about 40%. It's just not safe for our grid to take on more renewables. So if you thought the problem we needed to solve was to build more wind turbines or install more solar panels, unfortunately that isn't the case. Times are changing. In the US, the amount of electric vehicles sold nearly doubled last year. It went from 200,000 to just over 360,000. Worldwide, EVs are up about 64% year on year. We're selling over 2 million electric vehicles last year. I think it's scheduled to be around 3 million or so this year. Pretty much all auto manufacturers have pledged to move to either fully electric or electric hybrid over the next 6 years, between now and 2025.
Sorry, you've just said that figure's meaningless without knowing what the market is for total number of vehicles. I mean, is that 50% of the total car market, or is it 5%? I don't want to be...
Sorry, it's just that the amount of EVs being sold is increasing. Yeah. You mean, is the total size of the market increasing?
More than nothing, or is it from 0 to 50%? The whole point is, what percentage of the market of cars is that saying? Tells us whether it's significant. Sorry to interrupt.
The total market size for cars in the UK is reasonably flat. So it's still a smallish percentage of the total market, but it's growing rapidly.
Okay.
I think, and by 2025, I think the point is that almost all new cars will either be fully electric or electric hybrid in some way. I think it seems pretty actually inconceivable at this point that beyond 2025, anybody here will be likely to buy a car that doesn't have a pretty substantial battery in it. And that might all sound really good, but actually that creates some pretty significant problems for the grid. So cars, a domestic car charger, most of the new ones coming out now tend to charge at around 22 kilowatts. That, in case you're unaware, is about the equivalent of having 12 kettles boiling. So when you plug in an electric car, it's the equivalent of having 12 kettles constantly boiling in your house. Electric vehicles are an order of magnitude more of a power drain than we've ever experienced before in a domestic setting. The predictions are that in the next 2.5 years, we will increase the amount of electric vehicles in this country by about 1 million. There are 30 million cars in the UK. So we'll have an extra 12 million kettles attached to the grid. All that energy used to come from petrol and diesel. You'd go and buy it, you get it out of the pump, and that's where all that energy came from. Now we're asking our grid to provide all that same energy. So it's time for a little bit of maths. Okay, so we've got 1 million electric vehicles. I'm going to assume, I'm happy to be challenged, I'm going to assume that around 70% of them will be plugged in at around 7 o'clock in the evening. When people come home, they plug in electric cars and go into the house. Most new chargers are coming out now around 22 kilowatts. That means at 7 o'clock on a weekday, there'll be 15 gigawatts more energy needed on our grid, if we want to keep the same distance between the amount of energy we can generate today and the amount of energy we use today. So I went on Wikipedia, which is always right, I think, and I had a quick look. And since 2010, 3 power stations have been built. Those power stations total about 3 gigawatts of energy. So it's 15 gigawatts from the cars coming on over the next 2 years, and we've built 3 in the last 8. We need 15 more power stations in the next 2.5 years if we want to keep the distance between our current peak generation capacity and our current peak demand the same. In fact, if the whole country switched to electric vehicles, we'd need 450 gigawatts of energy. Today, the whole country can generate at its max capacity. If we turn on every power station in the country, we can generate 80 gigawatts. So it seems a bit like maybe all this electrification could be a huge problem. If you combine this with our need to move to more renewable, intermittent sources, it compounds the problem. It gets even worse. So how can we go about solving this problem? I think we can start by exploring ideas of storing some of that renewable generation so that we can have access to it at times when we really need it. So really there are 2 different strategies for storing energy. There is the kind of grid scale storage, which means that you kind of put batteries next to the place where generation happens. So you have a wind farm, you stick batteries, 50 meters from it. And the other strategy is you have a domestic strategy where you have batteries in people's homes in some way. It's worth saying that the first one is by far the prevailing strategy today in this country and actually most countries across the world. So it's worth taking a moment to talk about this kind of centralized grid level strategy. So here is a picture of a solar farm in Australia. This is the batteries at the front here, and then solar panels as far as the eye can see behind. Sun hits the panels, it comes in, it gets stored in the batteries, and then depending on the needs of the grid, gets released at a different time. One of the nice things about this is that batteries actually have very quick response. So unlike coal and gas stations, which take a little bit of time to ramp up and down, you can turn these things on and off really quickly, actually. And this does help us solve the problem with flexibility of renewable generation. This could be deployed and rolled out to switch from 40% renewable to 100% renewable energy. It is achievable this way. But there's some problems with it. Batteries are still quite expensive. They've dropped in price quite a lot, but they're still pretty expensive going, and they deteriorate. And when you charge them up and down a lot, they deteriorate even faster. So you've got to really be confident that you can pay back this huge investment in batteries when you stick them in a big farm like this. There's another problem as well. And to understand that, we need to understand a little bit about how the price of energy is made up. So during off-peak times, the price of generation makes up the lion's share of what energy costs. So generation is about £40 a megawatt hour. Distribution is about £1.40. Distribution is kind of like the last mile stuff, like your local area. And transmission is like the big kind of countrywide network, the huge pylons that you see in the fields by the side of the motorway. So transmission can just be free in the middle of the day. Distribution, pretty cheap. Generation, £40 a megawatt hour. On peak, it's a very different story. So generation becomes nearly triply as expensive, but distribution goes up by 100 times. It's worth saying this is the most extreme example in the country, which I believe is the southwest, maybe here. And transmission goes up as well from 0 to 63, infinite times. So it's a pretty considerable change between off-peak and on-peak. And the problem with storing batteries next to where generation happens is that you still have to negotiate these expensive transmission and distribution costs. In fact, really the only savings you're getting is this price and generation difference between off-peak and on-peak.
Hi there. The distribution and transmission costs, are they just a pricing feature, or do they reflect real cost? In other words, are you just paying for plant over years? Somebody has to pay sometime, or is it a real variable cost?
It's a good question. I think it is a real variable cost in that at these points the grid becomes under a lot of stress. I want to disincentivize more energy coming onto the grid beyond a certain point. But of course, but I think it's a little bit blended as well, to be honest, because there's a huge capex investment, obviously, in putting together the grid, and the idea that transmission is free off-peak obviously isn't quite true. So I think the actual answer is a slight blend of the two. If that makes sense. So if you're spending a lot of money on batteries on a solar farm, and you want to be confident that it's going to pay itself back, but you don't have access to any of the savings that distribution and transmission could make, maybe you're in a bit of trouble. Maybe you're not. Who knows? So the other strategy then is storing energy in people's homes. Storage in homes brings about the same benefits that happens in grid-level storage, in the sense that it means we can increase the amount of renewable generation that occurs, and it means that you offset those generation costs between off-peak and on-peak. But you also get access to all those savings of transmission costs, because we can transfer the energy into people's homes at off-peak times, keep it there, store it there. And then actually at on-peak times, you can push it back out into the grid and make some money, or you can just use it in your home internally. It's pretty awesome. It's pretty cool stuff. But batteries, in fact, suffer a similar sort of problem that we were talking about batteries before. Batteries are actually really expensive still. By the way, that's an OVO battery. It's cheaper than a Tesla one. But they're still, it is quite big. But the Tesla one's pretty big as well. It's maybe like there by that. Yeah. You want a double garage for that, I think. Yeah. Sorry? Loft, yeah. They're pretty expensive, to go, but they're just on the verge of economically viable, to be honest. They pay themselves back just over like a 4 or 5 year time period. I think it's a really exciting area, and it's continuing to get better and better and better. But actually, it's probably not the area that I'm really excited about, if I'm honest. Back to these pesky electric vehicles coming on the grid all the time, these 12 million kettles and grid-destroying electric vehicles. The interesting thing about cars is that we don't use them that much. We spend tens of thousands of pounds on cars, and we use them 5% of the time. 95% of the time, they're set around doing nothing. And they have huge batteries in them, actually much larger than an on-wall battery that you get from either Tesla or from OVO. So if we imagine at 7 o'clock, rather than us drawing down all that energy from the grid and destroying it and needing all this extra power that we talked about, what if we were pushing out energy onto the grid instead from our electric cars, from the spare charge that we had from our drive home from work? If we could control that charge somehow, pull it down when there's a lot of renewables, when it's sunny and windy, we could pull it down into our cars. And at times when there's less of that, we can push it back out. Maybe not only can we alleviate this problem with needing a lot of energy from electric vehicles, but maybe we can also support the incremental rollout of renewable energy, both in the UK and potentially globally. But to do that, we need some things. First of all, you need a super smart charger. You need something which is tapped into the price of wholesale and the situation on the grid, the frequency of the grid. It needs to be able to both charge and discharge. So you need an electric vehicle charger which can take energy out of your car and push it back either into your home or to the grid. Luckily, OVO has built the world's first widely available domestic bidirectional charger. Just a Nissan Leaf right now. But it is worth saying, I don't want this to be an OVO spiel, other versions of these are coming along this year as well from other manufacturers as well. I think it's an important change that needs to happen, whether it's OVO or anybody else. I think it's important when this transition happens that people have a lot of confidence in the way this works, and setting charging schedules are important, so you know that you have 100% charge for the morning, and there's always at least 100 miles or whatever there is in your battery, so you can go about dealing with any emergency situations. But I think this is really interesting to me because unlike batteries, people aren't buying electric vehicles for the storage. People are buying electric vehicles because they're becoming better than combustion engine cars. And rather than all that time when they're sat around doing nothing, actually, if you plug it in, you can be part of a movement which helps to increase the amount of renewable generation and make money from it, maybe get free energy, maybe free charging for your car. I think it's a pretty interesting proposition. But it's not all plain sailing. So the disadvantage of this is that you end up with thousands, tens of thousands, millions of connected IoT devices. And it's not Pokemon Go. You know, people's lives depend on this, or maybe people's lives depend on Pokemon Go. But this is pretty important stuff, right? People need to be confident that their cars or batteries or whatever it is are charged up at the right time when they need it. You can't make that many mistakes. And people also need to understand how economically they're benefiting from this, right? Or environmentally benefiting from this. So we've got a large distributed system. It's finally time for us to talk about Kafka. Quick show of hands, who here has used Kafka before? Okay, quick show of hands, who here has used Kafka in production at scale? Okay, cool. All right. Quick show of hands, who knows what Kafka is? Okay. Quick recap. It's lucky you didn't all put your hands up, by the way, otherwise I would have had to whiz through all of these. So Kafka is just an append log. It just adds data to an end of a file. So we just keep adding data blobs after data blobs. It organizes data into topics. So this might be a payments topic, and it's a list of payments that have occurred. It's unlikely the data would just be like an integer like this. Normally it's some kind of more detailed data structure that tends to be keyed in some way, like maybe on a customer ID or whatever it is. The interesting thing about Kafka is that it's really simple and that it's just an append-only log, but also that it's highly distributed, and that's important. So what happens in Kafka actually is that depending on your primary key, we split the data across different partitions. So certain customers will be writing to one physical virtual box, and other customers will be writing to another box. That's important because what that means is that we can scale writes horizontally. And when you want to do a lot of writes, and LinkedIn do something like 4 trillion a day on Kafka, you want to be able to scale it horizontally. So partitioning, super important for writing quickly, but it's also important for resilience. So one of the things that we do with Kafka is, as we have more and more nodes, we might have these partitions spread across these nodes, but we'll also replicate partitions across nodes as well. So that means that if a node blows up, we can fall back from here, like node 1, we might be reading that partition 1 on, but as node 1 destroyed, we can read partition 1 off node 3. So highly scalable, highly fault tolerant, pretty dumb, in a good way. So when I think about the benefits Kafka brings to solving these sorts of problems, I think the 3 main ones that come to mind is that its ability to receive and process large amounts of IoT data, its ability to democratize data, and its ability to enable team velocity. So if we talk about IoT, so we've got all these chargers in the field. What's great about Kafka is that we can write to it super quickly. So lots of IoT devices can just come on in, connect into Kafka. We can partition as much as we like. We can scale our writes horizontally. And no matter how many, almost no matter how many devices we have in the field, we can keep scaling Kafka and write more and more and more data to it. Pretty handy stuff. And we can get them to report data on like a sub-second basis. The other thing we can do with something like Kafka is we can receive all this IoT data, but we can also start mixing in other important bits of information, like what the weather's doing, what the price of the wholesale market's doing right now, and other things. And we can process all that information, make some decisions about what should be charging, what should be discharging based on customer settings and these parameters, and then tell an electric vehicle charger to either charge or discharge or do nothing. Actually, lesson learned that we did, which was a mistake, when we first started connecting IoT items to our Kafka cluster, we'd receive items and do a little bit of pre-processing before putting data on Kafka. Don't do that. That is much less scalable than just putting it on Kafka, picking it up, stream processing it, making some decisions later on, and then informing Kafka back in. One of the really nice things about Kafka is this kind of like compartmentalization of performance characteristics. So writing data from IoT, you might have hundreds of thousands, millions of devices reporting data at a sub-second basis, but you might have one of these processes that hangs off Kafka that just doesn't need to perform like that. When you're coupled via HTTP, if somebody receives something and an HTTP call goes out, you're kind of coupling systems together about the way their performance needs to deal with problems. But here, actually, some systems can work slowly, if that's the way they want to work, and other systems can look at really fine-grained data and work in that way, if that's the way they need to work. Democratization of data. So I think one of the biggest problems, actually, with distributed designs is getting data back together again. And as far as I'm aware, maybe I'm wrong, there aren't super clear strategies for this. Most people I talk to has a slightly different way, different approach for bringing data back together again in certain microservice deployments. So one common strategy, this is the thing that people do, data comes directly out of the databases. Sometimes your kind of data team might go and pull data out of your databases and your microservices, bring it all together and stick it in some kind of data warehouse. There's quite a lot of effort involved in doing this process. And because there's quite a lot of effort involved in doing this process, it means that if you want to bring data together, you tend to do it in the place that you've put all the effort in to bring the data together that one time, right? So if we want to do clever stuff in here, we're probably going to do it in our data warehouse. A little bit of processing, take these kind of individual data sets, bring them together, get something. The gold is sort of indicating the valuable data. Do you see? It's done with color. And the problem we've got here, though, is that we're kind of stuck in our data warehouse. Right? It's not particularly democratic. You're stuck with two options here, really. You kind of say, actually, we're going to open up our data warehouse for operational purposes, which, by the way, data warehouse is not really designed for that sort of thing, right? Like web performance, data warehouses tend to not be. Or you close it all down and you don't have access to these valuable data entities. So what's the alternate option? If all your services in your distributed system are pushing data onto Kafka, you can do all that processing just straight off Kafka. Create those valuable data entities off Kafka, publish them back onto Kafka. And then it doesn't mean you can't have a data warehouse. You can have your data warehouse reading all that data straight off Kafka. We've built some interesting tools to kind of auto-ingest data straight off Kafka and put it into a data warehouse without having to do any kind of custom logic. It's quite interesting stuff. So, lastly, I want to talk about how Kafka can enable team velocity. And I probably think that this is the most important point, actually. And I think one of the driving factors originally for why we started using Kafka. I think the thing that's always interested me is actually that intersection between technology and behavior and people, and how certain types of technology, certain structures that you have in your organization map and change behaviors or the way people think about problems. People tend to talk about, I'm sure you hear a lot, it's become a bit of a cliche in technology, about team autonomy. People talk about it all the time. I think that probably we've decided as technologists that autonomy translates to better productivity, more velocity, more change. But it's a pretty easy thing to say, but I think it's maybe not so easy to actually do. Like, what do we mean by that? Like, how do we create autonomy for people? How do we create independence for people? And I think a really important part of that is that you're technically decoupled. You can't just say it. If you're not technically decoupled, it's pretty difficult to really be autonomous and independent. I think that Kafka can be a really important structure to help decouple teams from each other. That layer of indirection between teams and the ability to make data available for teams helps teams to be separate from each other. And that separate doesn't have to mean they don't talk to each other. It just means that they don't have to talk to each other. And I think that that's an important difference. I think this was actually like the original point of microservices, wasn't it? It was like more decoupling between systems in lots of ways, independent performance profiles of systems. And I think that microservices that operate in a more reactive way help take that step further by actually creating more decoupling of data modeling as well. So let's have a little look at how that might work a little bit, more kind of independence of data modeling. We could have a team, like an identity team, that are publishing out information on customers, things like names, first name, last name, email address, that kind of stuff. And if another team, our comms team, wanted to use that data, they could take that data off Kafka and they could store it locally within their own domain. They could take a copy of that and keep it in their own domain. That means that if the comms team do something with that data which is some peculiar performance characteristic, the identity team does not need to respond to that peculiar performance characteristic. Additionally, it means that if the identity team just explodes overnight, then the comms team can continue to do its thing. It creates resilience through independence. I think, like I said before, I think it's probably, for me, one of the most important elements is this kind of team decoupling. And I think when we look back in OVO, how far we've come, and this is difficult because there are lots of things that we've changed. We've done a kind of piece of work over the past year where we try and compare like-for-like projects. This is obviously not exactly scientific. It cannot be done that way. But we try and do this, just trying to see like things that we think look similar or projects where we worked on a similar sort of thing, and how have we changed? How has our ability to make change changed? And we've seen when we do comparisons somewhere between 5 and 10x improvements in the rate at which we make change now versus 3 years ago. Actually, before I get off this section, I would like to make maybe a slightly controversial statement, which is, I think at this point I am not convinced that microservices that communicate exclusively via point-to-point communication or HTTP are much better than large monolithic systems. Controversial point to talk about afterwards. But Kafka also has a whole load of challenges, actually. And here's some of the ones that we've faced. So the operational overhead of Kafka, the ecosystem maturity, and data regulation. I mean, it wouldn't be a fun tech talk without some data regulation. So when we first started out with Kafka, we decided to run it ourselves, and we did a proof of concept. We prototyped it. We liked the look of it. We thought it seemed pretty easy to do. And then we started scaling it, and we had to start doing updates, and we had to start thinking about 24/7 support, and we had outages. And we realized pretty quickly that maybe we didn't like the idea of running our own Kafka cluster. And I spoke to a few people that work in other companies that were running Kafka at pretty big scale, and they were telling me that they had teams of 8, 9 people exclusively running their Kafka clusters. And we thought, we probably don't want to do that ourselves. So we went and switched to a managed service. We use a company called Avon, if you're interested. And I think it hasn't been plain sailing, but on balance, I think better than doing it ourselves. So lesson number 1 was, don't run Kafka clusters yourself unless you really want to. Secondly, this ecosystem and knowledge maturity. Actually, I was, before I came here this evening, I spoke to one of my colleagues and said, what do you think the challenges were with Kafka? And he came up with a whole bunch of list of things, of problems that we've had, and I think every single one of them came down to this. That's the ecosystem maturity. I don't necessarily just mean about Kafka itself. I mean the libraries that sit around Kafka and the tooling that's available. So yeah, I think it's maybe in a slight teenager phase. I think we've encountered technical problems, like when we originally switched to Avon, we use a schema registry as well. We use Avro on Kafka. We have a registry for all our Avro schemas. When we first did that, and we had a big authentication problem. None of the libraries that we were using supported authentication. We've had problems getting logical types in K tables, which is a way of representing data in Kafka that's kind of, so you can query it in a more SQL-like way. We have problems with log compaction, which is another feature I'm going to touch on in a little second. So we've had technical problems. There are kind of missed opportunities in tooling that are less like burning problems, but more just life would be easier if we had. Like we built our own auto-ingestion capability to take data out of Kafka and put it in a database. Kafka is great, but it comes with more engineering overhead all the time. If you just want to take that data off a topic, put it in a database, and put an API on top of it so you can access it, it's a lot of engineering, and you don't want to do it every time. It would be great if there was some tooling to just say, I want this topic in this type of database, please. That would be really handy. And I think the other thing is like people's mindset. Actually, I think streaming and reactive systems is becoming more and more common and more popular, but I still don't think it's the prevailing way that systems work. So there's a little bit of a mindset change there needed for people that come into these sorts of systems. There's a lot of new techniques and challenges that come with that, and that needs the right kind of communities and support and training for people to kind of get into the right place with that. So the fun one, GDPR, who doesn't want to end on a high? And I think when we originally started using Kafka, we had all these grand ambitions of infinite retention on topics, and we were going to use it for grand elaborate event sourcing and spending evenings on YouTube, watching all of this stuff, and getting super excited about it because everyone in the US, you know, if you go on YouTube, you read stuff, it's all in the US, and they do not have GDPR, so you get overexcited about it all. Even Confluent themselves say, like, you should be storing data in Kafka, it's great for it, it's really good at it, you should do it. So we got really excited about it, and then it all came crashing down, because actually, really, Kafka's simplicity comes from the fact that you can only really append data. That's what you do, you keep adding data. There's no real mechanism for going back and saying, this old data I told you about, could you kind of get rid of that, please? It doesn't like that. And that is a real problem with GDPR. So you can't really do that. You can't store long life event streams on Kafka, no matter how many YouTube videos you watch about it. And it means you've got to take it off and put it in a database if that's what you want to do with it. We have shifted our strategy a little bit, and we are now using the log compaction feature in Kafka, which kind of means that rather than storing a big stream of events, we're able to kind of publish more like stateful entities onto Kafka, and we're able to overwrite them the whole time. So we keep overwriting, and by doing that, we can overwrite with kind of like a blank entity if we want to kind of, remove data from somebody. So it's a slightly different technique, but it brings us the data availability elements of Kafka. It means that everybody can have access to those entities.
Obviously, there's a delay before that compaction happens. Say you tombstone something with this delay. What sort of delay tends to be acceptable with your own GDPR guys?
I do not know the answer to that question.
30 days.
Sorry?
I think it's 30 days.
Here we go. Thank you, guys. I would say that on balance, Kafka has been a good story for us, and I think it matches our problems pretty well. I think it's something that we would do again if we had the choice. I would say it's not without challenges, and I would say that it actually does add some complexity. I wouldn't recommend it if you're in a startup and you've got just a couple of systems you want to stitch together. I don't think it's the right tool for that job. But I think beyond a certain scale, beyond a certain kind of system complexity, I think it helps to reduce some of that complexity. And I would like to leave you on a note that I think even though a lot of some of these solutions that we talked about around the grid are kind of coming in the future, the problem of climate change is very much real and very much now. So in between now and those moments where technology hopefully helps to bring about a brighter future, I'd like to ask you to all do your own bit in helping to make the Earth a slightly better place. Thank you very much.
Could you give us an idea of how many teams, software engineering teams, do you have? And how many do you actually use Kafka?
We have 45 product engineering teams, and I don't know, the majority use Kafka. Maybe like there's maybe a few that don't. There's definitely a few that don't. Maybe 40 teams use Kafka.
I just wanted to ask, have you also done some kind of geeky calculations about how many batteries you think all these electric cars might need and whether we've actually got the raw materials to make them?
That's an interesting point. Like, is there enough lithium in I hear there's quite a lot of lithium, but maybe the price of it's going to go up as mining gets harder. Right. Yeah.
There are cobalt-free batteries.
There we go.
Sorry, could you repeat the question?
Sorry, Chris. I knew that was going to happen. I was going to say to you before I came up, you're going to have to remind me basically every time to do that.
That's fine.
Just a question on Kafka. Did you choose Kafka off the bat, or did you compare different queuing systems? Because a lot of this might be general advantages of queuing systems.
Yes. So the question is whether or not we did like a comparison between Kafka and other queuing systems. The answer is yes, we did do a comparison between Kafka and a number of other queuing systems, pretty much all the big ones. And I think you're right. A lot of the advantages that we're talking about, like the architectural advantages, are true for all queuing systems. Are true for most queuing systems. Some queuing systems have more logic in them, like Rabbit, for example. There's obviously a performance compromise to some of those other elements of features that it brings in, but there are now like cloud-hosted systems that mimic Kafka's design patterns. And I think it's probably fair to say that a lot of these advantages are true for a lot of those Kafka-esque style queuing systems.
So you mentioned the word reactive there a few times. I'm going through a bit of a battle with the CTO at the moment about even adopting Kafka. But have you used the more reactive style of Kafka, or is it just a standard library that you've used?
We have used we've been through lots of different libraries. In fact, one of the things I was going to do in the maturity section originally was on some of the libraries that we've used and burned. But yes, we use a lot of Scala and Clojure internally. And we've been through some Scala libraries. We use the Akka library and do not use the Akka library anymore. Apparently the guy, the Akka guy, was like, oh God, no, don't use that. No, I just did that on the weekend. And I said, everyone's using it. you gotta tell people. So we've written our own, we have the author for FS2. I don't know if anyone's familiar with FS2. We have the author of FS2 that works with us. And the team have built this new FS2 Kafka library, which seems to be resilient at the moment.
Open source?
It is open source, yeah. Yeah, you can check it out. Yeah, are you Scala?
No.
Okay, well, if I switch to Scala, use FS2 Kafka, and you're fine. Yeah, but we've used a bunch of different libraries. Some of them we've had not a lot of success with and end up rolling our own. And I think that's, again, highlights this maturity point a little bit. Did I repeat the question? I didn't, did I?
Never mind.
Like on the cars, if there's a general trend toward people not owning their own cars and cars just being commoditized, does that break your model in some way for distributed storage?
I don't think so. It might make the storage a bit more centralized in some way. They will go somewhere when they're not being used. So maybe it depends what level of utilization, but they will have to be plugged in and charged at some point. If we get to the point where utilization is so high that they are only, when they are plugged in and charging, they have to be charging at max capacity in order to get back out again, then maybe, yeah. But I suspect by that point, the price of batteries would have dropped so that you can switch back to like a home battery storage strategy.
I heard somewhere that we're already pushing a lot of energy to Norway because they've got better facilities for hydropower storage. Is that happening? Do we do that?
I do not know the answer to that question. The question is about whether or not we are pushing energy to Norway because they have better, like, what storage capabilities.
Hydropower,
Yeah. I don't know if that's the case.
We already do it in the UK to a certain extent. Got two.
Yeah.
Losses to Norway. Wow.
Yeah.
Yeah, somebody said, I faintly remember this, that there's a massive undersea cable that goes across.
We do export and import energy. Yeah. Generally, but I don't know about Norway specifically. For
This was specifically for storage. So
right.
I think to
Right.
solve that
Yeah.
problem, so
We do. There are definitely, like, we do have some storage capabilities, which tend to be hydro, but it's not a lot. It's not enough.
Does it make sense to use your car battery as this storage every night for the longevity of the battery? Is it economically viable?
So we are doing a lot of research on this right now, and it would seem that rapid charging, so you probably know this from your phones, but like where you don't want to be charging is at like 99%, 100%, and 0 and 1. You don't want to be at the kind of extremes, you kind of want to be in the middle. And actually rapid charging, some research is showing that rapid charging can extend lifetime if you're in the middle. It can actually clear the cathode and anode a little bit from some of the debris which causes battery degradation. But longer, bigger swathes of charging can be degrading to batteries. So I think the important thing is, so with Nissan, for example, our partnership with Nissan, we have deliberately worked with them around their battery warranty to make sure that the charging that we do is in line with their warranty, so the battery warranty is still valid. And I think that's really what we have to do. I think the other option is that you shift to a leasing model of cars and people are less worried. You know, if the person doing the charging is also the person leasing the car, you kind of back your own charging capabilities. I think it's a big consumer concern, I would say that. The biggest consumer concern is what will happen to my battery.
What all other areas Kafka can we utilize Kafka systems?
Other areas, I would say a lot of real-time use cases it's quite applicable for, but I would say that there's a team size and problem set size threshold that I think you should probably overcome before doing it. So I think that it's a good tool for lots of different problems where you're interested in lots of data, lots of write data, you're interested in systems responding to other systems. I think it's good for all of that. I know it's a bit general, but I think it's quite a general tool. Okay, I think that's all I can do. So thank you all so much. It was lovely to come and talk to you all.